students, in the last class I have taken the different types of electronic transitions, namely N to 5 star transition, N to sigma star transition, 5 to 5 star transition, and sigma to sigma star transitions. And I told you the meaning of these kinds of transitions also. The order of energy required for these transitions is in the order as given in the figure. That is, N to 5 star transition requires lowest energy than the pi to 5 star transition. Like this, the sigma to sigma star transition requires higher amount of energy. So because of this, the wavelength required to excite the electrons from sigma bonding orbital to sigma star bonding orbital will be the highest. Hence, the wavelength at which this transition occurs is around 150 nanometers. So try to recall the wavelength range that I have given you for UV, for UV region and the UV region. So the far UV region is from 100 to 200 nanometers. Hence, these two kinds of transitions, sigma to sigma star transition and pi to sigma star transition, they occur in the far UV region, and this kind of transition occurs in the molecules containing pi bond and the sigma bond. So, this region of UV spectroscopy is also called as vacuum UV spectroscopy, which is not that much considered in the study of UV spectra. The important region that we consider in this study is from 200 to 400 nanometers. That is why in this region of wavelength, the two types of transitions will exist, that is pi to 5 star transition and N to 5 star transition. Among them, the N to 5 star transition requires less energy, hence it occurs at higher wavelength, since energy is inversely proportional to the wavelength. And the 5 to 5 star transition requires the higher amount of energy, and the molecules having non-bonding electrons and pi electrons will give this kind of transitions. That is why the molecules with pi bond and non-bonding electrons are used to study in UV spectroscopy. You can see from this figure also, the ground state contains sigma bonding electron, pi bonding electron and non-bonding electrons, and the excited state, the antibonding level, contains pi star antibonding molecular orbital and sigma star antibonding molecular orbital. Among these two, pi star antibonding molecular orbital will be of lower energy than the sigma antibonding molecular orbital. Hence, the two transitions, namely pi to 5 star and sigma to N to 5 star transitions, these are the two types of transitions that we study in the electronic spectroscopy. Okay, so with this knowledge, now we shall take up some individual compounds. Look at this. It is ethylene, which has one pi bond, only one pi bond, and it has pi electrons. Due to this, this molecule will exhibit pi to 5 star electronic transition, and this transition occurs at a wavelength of 165 nanometer. See the value, 165 nanometer with an epsilon value of 1500. So the next compound, 1,3-butadiene, which has two pi bonds at conjugate position, that is, after one sigma bond, again we have pi bond. So this kind of arrangement is called as conjugated double bonds. In 1,3-butadiene, we have two double bonds at conjugated position, and this molecule also has pi electrons, and these pi electrons will absorb the wavelength at 217 nanometers, and see the epsilon value, it has been increased, means the peak height will increase, and there is a shift in the lambda max value towards the higher wavelength. With this, now take the 1, 3, 5 hexatriene. There are 3 pi bonds at conjugated position, and here again there is an increase in the lambda max value. Along with that, the peak height also has been increased. So with this, we can see that as the number of conjugated double bond increases in a molecule, I repeat the word, as the alternate double bonds, single and double bonds increase in a molecule, the lambda max value will shift to higher wavelength. Simultaneously, there is an increase in the epsilon value. So, to reason this observation, we can see this figure. That is, all these molecules will undergo pi to 5 star transition, but as the number of conjugated double bonds, the alternate single and double bonds increase in a molecule, the gap between pi bonding orbital to 5 star anti-bonding molecular orbital will go on decreasing. And this is due to the fact that when there are conjugated double bonds, they undergo resonance, hence the energy required to excite the electrons will decrease. In other words, these transitions will occur at higher wavelength, which requires less energy. So this is the skeleton of 1,3,5 hexatriene, in which due to the resonating structures that exist in this molecule due to the delocalization of pi electrons will bring down the gap between the bonding molecular orbital and anti-bonding molecular orbital, and that is why the energy required is still less. That is, the wavelength absorbed for this molecule will increase. I think you have understood this concept with reference to these values. And this kind of conjugation will increase the lambda max value. Simultaneously, there is an increase in the epsilon value. So, look at these molecules. These are the simple molecules which have simple structures, and when you compare the structure with the lambda max value, you can understand that as there is a change in the structure, there is a change in the lambda max value. Simultaneously, there is a change in the epsilon, molar extension coefficient value. Hence, these are the two theoretical values, physical values, which are reported in the UV spectroscopy for each molecule. The position of the lambda max will give you the nature of the bond present in the molecule, and the epsilon value will give you the extent of conjugation in the molecule. Similarly, in case of benzene, this is the lambda max value at 255 nanometers. When there is a increase in the number of rings, fused rings, in case of naphthalene, due to the delocalization of these 5 pi bonds, the lambda max value has been shifted to higher wavelength, and in case of anthracene, it is still higher. And see the peak height also, it has also increased, and this peak height will refer to the epsilon value, and the wavelength corresponding to this will be lambda max value. Hence, as there is a change in the conjugation in a molecule, there is a shift in the lambda max towards the higher wavelength. So now we shall see the terms used in UV visible spectroscopy. So these are some of the terms frequently used to describe the nature of UV spectrum. The first one, chromophore. I think I already explained this term in the topic on dyes while discussing Witt's chromophore oxochrome theory. What I told you there, chromophore is a group with multiple bonds responsible for imparting the color. So there I have explained with reference to the functional group which is responsible for color of the compound. The same aspect holds good here also, but slightly it has a broader meaning. That is, chromophore is a unsaturated group or the group with multiple bonds which is capable of absorbing UV radiation. That is, energy is absorbed in the UV range. The examples here are the same functional groups: nitro group, nitroso, carbonyl, cyanide, then C2C double bond, C2S, etc. So look at these functional groups. They have invariably the double bond. Along with that, there are non-bonding electrons except C double bond C. Hence, all these functional groups exhibit N to 5 star transition and also pi to 5 star transition when it absorbs UV light, except this which gives only pi to 5 star electronic transition. When there is a absorption of light in the UV region, the electrons get excited and we will get the absorption spectrum of that particular molecule. And the position of the lambda max will give you the nature of the double bond present in a molecule. Okay, next, the oxochrome. So it is a functional group which is present along with chromophore, and it modifies the ability of chromophore to absorb light or alters the wavelength or intensity of the absorption. This word I have also discussed in the topic on dyes, which will change the color of a chromogene. To give you an example, benzene has lambda max value at 255 nanometer. Then look at this compound phenol, where OH group is attached to the benzene molecule by replacing one hydrogen. For this molecule, the lambda max is 270 nanometer. Then in case of aniline, which has NH2 group attached to benzene, the lambda max is 280 nanometer. That means in case of phenol, OH is the oxochrome. In case of aniline, NH2 is the oxochrome. The basic chromophore present is the double bond in the benzene ring. As the the oxochromes are attached to the chromogene or chromophore, there is a shift in the lambda max value for these molecules. So in case of aniline and aniline hydrochloride, so these are the better examples to explain the nature of chromophore and oxochrome. So in case of aniline, it is 280 nanometer, lambda max value is 280 nanometer, but when you add it into hydrochloric acid, it is converted into aniline hydrochloride, a salt, where the lone pair of electrons on the nitrogen has been utilized in forming a covalent bond with hydrogen. So there are no non-bonding electrons on the nitrogen now. Due to this, the conjugation will decrease and the lambda max value is now shifted to the lower wavelength instead of higher wavelength. And here we have given the examples of chromophores and the auxochromes. Now we shall see the bathochromic shift, or it is also called as intensity shift. So to explain the nature of UV spectroscopy, we frequently use these words. For example, bathochromic shift, in which the lambda max is shifted to higher wavelength, longer wavelength due to the attachment of auxochrome or the change in the structure. It is also called as redshift. So the bathochromic shift is occurring towards the higher wavelength region in this graph. Say this graph, wavelength is plotted along the x-axis and absorbance is plotted along the y-axis. If this is the actual compound, then the presence of auxochrome will increase the wavelength or lambda max for that particular compound, and this is called as redshift or bathochromic shift. The opposite of this is called as the blue shift, where the lambda max is shifted to the lower wavelength. So here I give you an example. In case of aniline, it is 280 nanometers, but the addition of hydrochloride will lower the lambda max value. So this is a hypsochromic shift, but here it is a bathochromic shift. That is, the addition of OH will increase the lambda max value. Then hyperchromic shift. So along with the bathochromic shift, sometimes there is an increase in the peak height or the epsilon value. This effect is called as hyperchromic effect. So here you can see the hyperchromic effect. With the increase in the number of double bonds, there is an increase in the value of epsilon, and this effect is called as the hyperchromic effect. The opposite of this is called as the hypsochromic effect. Hypochromic effect, where the intensity of absorption will decrease. So these are the four terms which are used to explain the shift in the position of the lambda max value with a change in the structure of the molecule or change in the solvent. So redshift is associated with the increase in the lambda max value, and blue shift is associated with the decrease in the lambda max value. Then hyperchromic shift is associated with the increase in the epsilon value, and hypochromic shift is associated with the decrease in the peak height or epsilon value. So if you remember this figure, it is very easy for you to explain these four kinds of shifts that are associated with the UV spectra. So here are some compounds which I have given as an example. You can see these structures. There are many number of conjugated bonds. Along with that, there are auxochromes. So as the number of conjugated double bonds increases, the lambda max value, the wavelength at which absorption takes place will decrease, and ultimately the absorption will occur in the visible region if there are higher number of chromophores, larger number of chromophores, and this is the reason why some of the compounds appear colored. Why the compounds appear colored? I told you in the topic on dyes, there are colored compounds, isn't it? And you have seen the structure of different dyes also with reference to their colors, and all those compounds have multiple bonds in the conjugated position. Along with that, they are also attached with the auxochromes. When the number of such groups increases, the wavelength absorbed will decrease and it will fall into the visible region Therefore, the compounds appear colored. And this is the basis of the topic on dyes. Okay. With this, I will conclude today's class, and in the next class, I am going to give you some problems associated with the calculation of lambda max value. For that, I will send a chart containing some datas that you have to bear with you. Then I will teach you how to do the calculations for the molecules with the help of those charts. So with this, I will conclude today's class. We shall again discuss the remaining things in the next class. Thank you.